Hi, good morning there in Valparaíso, Chile. Oh, well, good afternoon, good evening, night, depending on where you are watching this video. Well, my name is Francisco Cruz. I work at Deakin University as a research fellow. I'm currently now in Australia. So, well, before starting, I would like to thank the organizer for inviting me to giving this talk. I think it's a very nice idea to have a summer school, a Latin American summer school on cognitive robotics. So it's somehow a good opportunity to get to know to each other, people interested in the same area. So I'm quite happy to participate in the first edition of Lakoro. Thank you one more time. So now, well, I'm gonna try my best to record this in one shot. Not sure if I can make it. Well, if I need to restart in some point, you will realize because there will be a cut in the video. I'm gonna share now the presentation. Yeah, so now you should have been seeing the first slide. I hope so. Let me just make just an adjustment here, like this. Okay. So, well, my presentation today is called explainable robotic system in reinforcement learning scenarios. Well, since this is a summer school, I have been told that it would be interesting as well to have a initial slide like explaining the main or the basics ideas of the approach. So actually my presentation is divided in three parts. The first one is just basics concepts of reinforcement learning, starting in the most basic ideas even. And then after I'm gonna show you an explainable, a memory-based explainable reinforcement learning approach, working well in a small grid war scenario. And thereafter, the third part is like an extension of the previous approach, where we use we use this in a robotic scenario. Well, the idea is to have this the robot giving human-like explanation in order to be more interpretable the actions that the robot perform in an environment. Okay. Well, as just mentioned, the first part is just the introduction about reinforcement learning. So, well, for the ones who are already familiar with the approach, probably that could be just a refresh. For the ones who are not familiar with the approach, should be absolutely necessary because there are going to be concepts here that are going to be used later on in the rest of the presentation. So anyway, I just have the idea of spend like, I don't know, 10 minutes in this part. So I'm going to probably go through sort of fast. Well, the first thing that I would like to mention are like initial ideas. In this sense, I need to mention one of the laws of association from Aristotle, which is the contiguity law. Well, it says things that occur near each other in time or space are readily associated. Well, of course, this is not precisely reinforcement learning, but if you look at this in perspective from what we know today about reinforcement learning, that makes absolutely sense. And because we know now that this in fact happen in reinforcement learning. The interesting thing is, well, there were people like so many years ago thinking about this and trying to formalize this thought in these ideas or this law, sorry. Okay. Well, a big jump in time. So last century, beginning of the last century, we have the experiments performed by Pavlov. Probably most of you already have heard about this. Again, this is not exactly reinforcement learning, but I think that is a very interesting idea, which somehow influence later on in reinforcement learning as well. What Pavlov proposed is the classic conditioning, also known as Pavlovian conditioning, or stimulus response learning. The experiments of Pavlov consisted in giving an stimulus to his dogs. Well, he used an unconditioned stimulus, a piece of meat, and he observed that the dogs started to produce saliva. Okay, then after he tried the same using a neutral stimulus, a bell, and of course there was no response. The dogs didn't produce any saliva. Third, he combined these two stimulus, the unconditioned stimulus, the piece of meat, with the neutral one, the ball. Again, he observed that the dogs started to salivate, probably because of the meat. But what is interesting is what happened in the fourth part, that he started to make the bell ringing, and he observed that the dog had a conditioned response. Because in that moment, the bell ringing became a conditioned stimulus. In other words, the dogs like reminded about the food because of the noise of the bell. Okay. However, in this case, actually the stimulus response learning, it's more a reaction. The dogs reacted to something that reminded them the food. It's not that they decided to produce saliva. No, they just had a reaction about that. Okay. Slightly different to this other experiment performed by Thornicke, also beginning of the last century. He used cats in his case. So he put the cats in a box, and there was a mechanism that the cat could activate it in order to get out. And immediately outside there was a piece of there was a meal for the cat waiting for him. So what he observed is that over time, when the cats repeat and repeat, trying to get out, of course they were performing this faster and faster. The more they try, the faster they get out, because they want to get the food as fast as possible. But in this situation, it's a little bit different, because in the cat's case, there is a decision involved. The cats decided to activate the mechanisms in order to get out. So that's why it's like stimulus behavior learning. So it's slightly different to the case of Pavlov. It's not exactly the same. Well, in a big jump on time, well, from some years now, actually, we know that, well, reinforceable learning is associated with decision-making process which occur inside of animals and humans' brain. Okay, there is actually no only reinforceable learning in machine learning, but also exists actually in the human brain. No. It is a mechanism that we cognitive beings use for learning, actually. For instance, in infants, when they have pleasant feelings, the level of dopamine in the brain actually get higher. The dopamine is a neurotransmitter inside the brain. So as I said, it's associated with high levels of dopamine is associated with pleasant feelings. Okay. Also, the frontal cortex and the basal ganglia, which is right in the middle of the brain, play an important role in decision-making process. In this regard, well, taking neuroscience as a motivation, the basal ganglia has been modeled as an actor-critic version of temporal difference learning. The temporal difference learning is, well, one way that the reinforcement learning agents may learn from the environment as well. The decision-making process is actually shown in this figure. The yellow box represents the brain. So you have the world on the environment that is around you. You have a sensory processing. No, well, we use our different sense for that. Then in the brain, we make a decision about that. Therefore, we produce, well, we first generate a motor processing, which is transformed in motor actions. Somehow this motor action should modify our world. And then again, we start the sensory processing, decision making, motor processing, and so on and so on. Okay. Well, anyway, the idea of learning by interaction from the environment is not new. As I said, it's taken from human cognition, from human beings. We, in fact, learn in this way. Okay. Although it's not necessarily to have an instructor, you could have it. But in classic reinforcement learning, it's not mandatory. The thing is, there are many things that you can learn without any instruction, just by interacting with the environment. You just need to have, well, the awareness how the environment answered to the actions that you perform in it. Okay, so, well, again, this is the basic about reinforcement learning. I know it says there that no explicit instructor. However, there could be, I know, but also in reinforcement learning for machine learning, it's called interactive reinforcement learning. So it is an alternative for that. But in the most basic approach, no instruction is needed. Well, in the case of machines, the learning it's carried out like it's shown in this image. This is the classic loop for reinforcement learning agents, where, let me put the pointer, where here you have an agent in a particular state. From that state, the agent take an action in the environment and observes a new state and a reward signal. And then again and again and again. The point is this agent is constantly observing what happened after performing an action. This agent may learn a pattern about what state and actions are associated to improve this reward signal, which is the aim of a reinforcement learning agent. Try to collect the more possible reward over time. Okay, so at the very beginning, of course, maybe the agent doesn't know so much about the environment, so doesn't know what action is the best to perform. So it can be performed any, just sort of random action, and observe. But over time, when the agent is learning, of course, he can decide what action is better to perform in the environment, and in this way, to receive the more possible reward. Well, I want to show you a little example. This is taken from the SoftBank Robotics YouTube channel. Well, in this experiment, this robot, the Pepper robot, is playing a game trying to spread the base of this part. So, well, at the very beginning, there is a person show the robot how to perform this task, or to try to perform this task. Of course, in the first trials, the robot cannot complete the task, so start over and start over and start over. However, after some trials, like actually after 70 trials, then the ball hit a border of the base, and then a bit more. But after 100 trials, actually the robot is able to put the ball in the base, like this. What they did after is like test the trajectory. So they make the robot try again and again and again. Well, make it short. the robot tried now 10 times, and he is success in the 10 times that he tried to make, so he repeat the action. Okay. Of course, the task can be modeled as a reinforcement learning task, but what is behind a reinforcement learning approach? So the kind of problem that a reinforcement learning method can address is the problem, is a category of problems which are called Markov decision processes. This is the base for reinforcement learning. If you can model a problem like a Markov decision process, then for sure you can apply reinforcement learning. Again, that is not necessarily 100% true. There are partial observable problems and other things that, but in the most basic idea, if you can model a problem like an MDP, okay, you can apply reinforcement learning then. Okay, an MDP is a 4 tuple consisted of, well, S, which is the set of states that the agent can be. A is a set of actions which can be performed from these different states. Well, delta is the transition function, which, well, says when I perform an action A from the state S to what other states I'm gonna reach. And then we have the reward function, which also associate state and actions with a real number. Again, well, in this case, it's a number, but that actually could be a vector as well, like the one you see when it's used to decompose rewards, whatever. But at the most basic is a real number. Okay. Well, as we said before, how to decide what action to perform? Well, initially can be any, because we don't know the environment. We need to know the world in order to decide better. Okay. What we only have is a reward function, which posts the objectives, but still I don't know, or the robot doesn't know how to get those higher rewards. Okay. So it's very important to decide what action to perform. Well, there are different methods. I'm here summarizing two of the most used ones. The first one is the epsilon greedy method. Okay, well, when you use an epsilon greedy method, most of the time you decided to perform the best known action. Okay, this represents the action which theoretically produced the highest reward in some point of the learning. That with a probability 1 minus epsilon. Otherwise, I'm going to choose any action. Okay. Well, that is actually quite good, because a problem that reinforcement learning agents need to address is the exploitation balance of task. And then, well, in this regard, when I perform a sort of random action, allow the agent to explore new regions in the space of solutions. Because if the agents is all the time performing the same known best action, it's very likely that finish trap in a local minima. Okay. Another method uses the softmax method, which, well, actually order the different possible action with different probabilities using a Boltzmann distribution. One parameter here that is important is t, where t is a high value. That means that all the actions are equally probably of being selected. And when t it's approaching to 0, these methods becomes a greedy method. Okay, so that just perform the best known action. Okay. Well, the general algorithm for learning, well, using temporal difference is the one showing here. As you can see, well, first you choose an action, well, perform the action, observe the reward and the next state, choose a next action, well, update Q. Q is a value which associates the state and the action in terms of how much possible reward I can collect starting from that state performing an action. It is a value at the end. It's not referring only to the immediate reward, which is here. It's more aware about the future chances of collecting reward. Okay, so this is the at the end of the day, that's the important, the value. Okay, because there could be an action which produces very high immediate reward. However, that could lead to a region maybe where over time this reward decrease, then the value could be not so high. There are different methods to update these Q values. I'm not going to explain these equations here, but these are two of the most used methods, SARSA and Q-learning. Okay. Well, at the end, reinforcement learning, what it tries to do is to map situations to actions. Okay, so from one state, what action to perform. Okay, that it's known as find a policy. Okay. So, well, therefore, an agent should be able to sense the environment and see what actions affect this environment. Okay. As mentioned before, an important problem is the exploration-exploitation trade-off problem. Yeah, and well, agents need to find an effective way to balance that. As I said before, for instance, could be done by epsilon greedy method. Okay. Okay. Well, I know that this is a very brief introduction to reinforcement learning. Of course, if you need to know more about it, definitely you should have a look to the book of Sutton Barton. I think it's a very complete book, very interesting. Well, ideas there. Well, the second edition is just 2 years. From just two years ago. So I think there are a lot of new material there as well that it should be a mandatory lecture. So yeah. Well, now I'm gonna show you some three different approaches, but I'm gonna start first talking about explainable reinforcement learning. Well, the problem with reinforcement learning method, one of the problem, is the lack of visibility or understanding for end use. The thing is, in many occasions, not only reinforcement learning, but also in many other machine learning techniques, they work closely with users who are not necessarily experts in the field. So even though sometimes it's possible to explain the agent behavior using technical clues like the Q values, like algorithms, like mathematical equations, and so on, that is not necessarily meaningful for an end user who is not expert in the field. So what we propose here is a memory-based explainable reinforcement learning method. The idea is that the agent can explain why some decisions using more human-friendly language. Well, explainable reinforcement learning is part of or subfield of explainable artificial intelligence, with the general idea is provide black box artificial intelligence-based systems with the ability of giving more human understandable explanation, or human-like explanation. As I said before, we have to understand that non-expert end users are going to be involved in the loop, so somehow they need to understand as well, especially for instance when there is a problem, there is a fail, people need to understand why an agent decided to make something. Okay. So far, explainable artificial intelligence has been more focused in deep learning methods, which is no surprise because in general, artificial intelligence has been more dominated in the last year by deep learning. So to have more explainable artificial intelligence methods addressing deep learning models makes sense as well, no? In the field of explainable reinforcement learning, there are actually some things that, well, we understand differently than the general frame of explainable AI. Okay. Okay. In our case, in my particular case, I'm more focused in trying to explain the decision-making process. Okay. In this regard, in robotics particularly, the term of explainable agency has been used in order that a robot can explain why the decisions are taken. But again, focus on the decision-making process, because there are many occasions that these explanations are based in provide visual explanation. I mean, the robot may provide an explanation on in order what it's seeing in the moment. Okay, so well, that is particularly useful when you try to explain something using deep reinforcement learning, for instance. But it's not necessarily focusing the decision-making process. Okay. Well, in our memory-based explainable reinforcement learning approach, we want to determine two different things. The first is the probability of success. So what is the probability of complete the task given an action? And as well, what is the number of transitions needed in order to reach the goal state? Okay. So what we believe is if that we use the probability of success to explain to a non-experienced user that it's more human friendly that posing a Q value in front of you. I'm gonna give an example about that in a few slides as well. Well, I'm not gonna explain the whole algorithm. Well, you can always refer to the paper as well. But what I want to mention is that we have used episodic memory, which has been implemented as a list. So we have a list of transitions. The state action transitions are saved in this memory. And at the end, using the amount of transitions that reach the goal state and the total amount of transitions, we can compute the probability of success. So this is something that it is record all the time. What it means that at the very beginning, when the agent doesn't know so much about the environment, and therefore the actions are just selected kind of random. Okay, this probability of success, of course, doesn't reflect the real probability. As long as the agent is learning, this probability is gonna start to reflect more the real one, the real probability. Okay. Okay, we have tried this approach in a very simple experimental setup. It is a grid world, 3x4 grid world. And we have tried two different versions, a bounded one and unbounded one. The bounded one, so imagine that you have here a wall surrounding the world. So every time that the agent wants to step out, it's not possible because the wall doesn't allow that. In the unbounded, differently, the agent is allowed to step out. But in that case, the agent gets into the aversive region where, well, a negative reward or punishment is obtained. The four typical actions are allowed here, like down, up, right, left, or north, south, east, west, as you wish. Yeah. Well, some parameters of the experimental setup. Well, the reward function is 1 when the agent reach the goal position, this one. And in the case of the aversive region is -1. We have used the SARSA method and softmax action selection method for the training of 100 agents. The learning rate was 0.3, the discount factor 0.9, and the temperature 0.25, the initial one. Okay. Well, regardless, these parameters actually, they are not that relevant for our approach. We are not looking, well, first we know that we are not dealing with a complicated problem. It's actually quite easy. But we are not interested in improving the speed of the learning agent. Instead, we want to understand why some decisions were taken by this agent. So it's not really so much relevant, these parameters. Of course, we know that with those parameters, the agent is gonna converge to the goal state. But in the meantime, we want to know why some decisions were taken in that way. Okay. Well, first, when we use the unbounded grid work, well, we are showing here the Q values and the softmax values, also the probability of success. Okay. Well, what is interesting to see here is first that the Q values are represented in the domain of the reward function. Okay, remember that the reward function varies between -1 and 1. So that is exactly the variability of the Q values. Not the same situation with the probability of success. But what is more interesting is, for instance, if you look at this region in the Q values and the same region in the probability of success, here it seems that, well, these actions are punished a lot. No, there is not so much reward in performing these actions. But for instance, if we take this, the action number 5, sorry, not the action, the state number 5, and the action up. So you are here, and you want to go up. If you see here, there is still a probability of being success, which makes sense because even though if you are here and then step to this state, you still can complete successfully the task. Of course, I know it's going to be a longer path, but that doesn't mean that you're not going to be successful. Well, this is reflected quite nice here in the probability of success computed from the memory, because that means that actually that happened. In some point, the agent decided to go up, but then turn to the right and go towards the goal state. But here is not reflected at all. Well, the softmax values are actually very similar, well, in another scale, but very similar to the Q values. It's another scale, of course, because this represents something different. This the softmax values represent probabilities of being chosen. So that makes sense that this probability is between 0 and 1. But yes, this is not the probability of being success. It's the probability of being choose. So this action in this state is actually really not so much probably that the agent choose. But still, if it is chosen, there is a probability of being success. Well, this figure what shows is well, the number of transitions. Of course, when we have the unbounded grid work, at the very beginning, there are not going to be many actions performed because probably quickly the agents step out of the environment. But as long as, well, this agent keep inside and doesn't step out, the number of actions will start to increase, and then after to decrease again, because there is a point when in the episodes where the agent learned the fastest route to the goal state. Okay. Well, given this context, one possible question that we could ask to the agent is the following. Why did you choose action down when in a state 0? So being here, why going down? So one way to explain this could be using the Q values. If we use the Q values, we have to show this information to the user, or maybe to say that, okay, the Q value in a state 0 for action down is minus 0.181, which definitely is meaningless for a non-expert end user. Well, if you know about reinforcement learning, well, you can see all others Q values, and you will see that this is the highest one. So actually it makes sense to perform this action. Okay. However, what if we use, instead of using the Q value or softmax probability, we use the probability of success that we just have computed? We can answer the question saying, okay, I choose to go down because that has a 73.6% probability of successfully reaching the goal. And these are the values, actually. It is 73.6 is taken from there. Okay, so this probability can be quite useful in order to better or more clearly explain why the agent decided to perform an action in a particular state. Okay, it's a more human-friendly explanation that using these values. As I said before, these values, they do explain the behavior, but it's a technical explanation. Okay. Another question could be, why did you not choose to go left when in state 0? Again, having a look to the Q values, no meaning. But using the probability of success, you can say, I did not choose left because that has a 0 probability of success. Actually, you can stop the explanation there. Sure, if you see the probability of being left is going left, is 0. If I show this Q value, doesn't make sense. Again, I mean, since you know about, maybe you know about reinforceable learning, and maybe you know the design behind of the problem, you could say, this value is really close to -1. So actually, probably the agent step into the aversive region. Sure. But again, people they don't have to know those details. So this is a much effective way to explain, I believe. Well, when we use the bounded grid word, in this case, we we have again the Q values, we have the softmax values, but then here the probability of success is computed in a different way. Why? Well, since we have a wall here surrounding the environment, the agent trying to reach the goal state is going to be always success, because the agent eventually is going to reach that state. Like wandering here, whatever, and in some point it's going to reach that position. So a better question here is the probability of success, but in a time window or action window. So for instance, here we have computed the probability of success in 8 actions, in 12 actions, and in 16 actions. So of course, the more actions, the higher probability to be in success. And in this case, well, just taking 8 actions takes a bit longer to reach the maximum amount of probability, which is related with the learning that the agent is carry out. Differently as before, well, here the number of transitions going immediately or quickly down. You start actually, maybe in a few chances, you reach quickly the goal state, but then after no, and then the number of transitions to reach the goal state start to decrease. Oh, I think I'm making this too long, so probably I'm gonna move quicker from now on. Well, a question that you could ask using this setup is, okay, what is the probability of finishing the task in 8 movements starting from the state 0? Again, Q values doesn't say anything. But if we use the number of transition, now we can say, okay, after 30 episodes, which means that the agent is still learning, the answer could be, I can finish the task in 8 movements with a probability of 39.4%. Or after 60 episodes, so that means that the agent has already learned more than in comparison with the previous approach, I can complete the task in 8 movements with a probability of 86.5. Of course, because I have been trained for longer. Okay, one last thing that I want to show you, it's about explainable robotic systems, which is basically an extension of the previous approach and using a simulated robotic scenario. So, well, the thing is, as I mentioned as well before, there are many explanations that are state-based explanation. No, so it's based in what is perceived. So, for instance, the explanation takes the form of I choose action A because of this particular feature F of the state. In the case of our goal-driven explanation, it's more like the one that we shown before, like I choose action A1 because has 85% chance of success the task compared to 38% for action A2. What is definitely not acceptable for a non-expert end user is explanation like this. I choose action A1 because it maximizes future collected reward. Doesn't say anything. Or I choose action A2 because it is the next one following the optimal policy. Again, it's not acceptable. For reinforcement learning practitioners, that is right. I mean, it's perfect. We understand what that means. But for an end user with no expertise, not really. So, well, as I said before, we extend the memory-based explainable reinforcement learning approach. So now we are going to, well, particularly to compute the probability of success. So we are going to have a robot performing a easy navigation task as well, learned by reinforcement learning. And this robot is, well, giving explanations to the end users, and in this way, trying to improve the understanding about the decisions taken. Well, the first extension is called learning-based approach. Well, the problem is, well, with the memory-based approach is, well, the dimensionality, or the, well, when the dimensionality of the problem is enlarged, more memory is needed. Okay, so it's not efficient in terms of use of resources. So then, what we have computed here is again the probability of success, but this time using a parallel table. Well, in our case, we are performing this in a tabular manner, but of course, if we use a continuous domain, this could also be another neural network in parallel. Okay, so a part of learning the action state Q values, we also learn the probability of success. Okay, the difference, if you see here the equation, is, well, two. First, there is a discount factor equal to 1. That's why it doesn't appear here. Being 1 means that this agent is going to try to consider all possible future rewards. In terms of learning, that's not a problem for the probability of success, because the agent is not learning with these values. It's learning with the Q values. Okay. And the other thing is, since the reward can be in another completely different domain, we here use a flag for, well, a success flag, indicating that when the task is done, this flag is equal to 1, otherwise it's 0. Okay, so when the task is complete, it's 1, otherwise 0. So the thing is, this reward can have different values on it. The second extension is called introspection-based approach. The idea is, well, even improve more the previous approach. The learning-based approach still requires a bit of memory, not that much, I know, but still some. But we believe, okay, what if we look directly to the internal Q values, and from there we compute the probability of success directly? Well, this has been done using mathematical transformation. Okay, these equations here. So what we know is that, well, the Q values are approximately the final reward or the total reward obtained times the discount factor to the power of n. In other words, if I know the total reward and I know the times that the discount factor was multiplied by that, I can obtain this parameter n. N indicate how far away is the agent to the reward. In other words, if the agent is in a particular state and know how many steps need to perform in order to reach the goal state, that would be n. Okay, so we obtain it from here. Okay, the point is n over time is a number which is decreasing. Okay, not like that. The probability of success has another shape. So that's why we have to perform this mathematical transformation I mentioned before. So if we weight this n value by this fixed number, is a fixed number, which represents a change in the base of the logarithm, we can compute from there the probability of success. This parameter here, well, sigma, refers to the level of stochasticity, which I will refer in the 1 or 2 more slides. Yeah, so at the moment, just ignore this. So what is important is that the probability of success is computed using basically directly the Q values. From the Q values, we obtain n, and from n, we can obtain the probability of success. Well, the experimental scenario in this case was a simulated robot scenario using the VROT simulator. We have used deterministic and stochastic transition. So when the agent is in this state, then we have, well, some rooms here that this robot need to reach the table here in this room to the right. So when the robot is transitioning these different rooms after performing an action, the robot can reach directly the right room, which would be a deterministic approach. But sometimes another state can be reached, which actually happen in real world scenarios as well. So that's why we have used here the stochastic transitions. Okay. The reward function is as before. We have a value of 1 when the robot complete the task, or -1 when the robot step out of the flow. Well, using deterministic transitions, well, we can see here the results. This is the probability of success from the state 0, the initial state here, for performing the actions left, right, or stay in the same room. Okay, left, right, and same. Well, what we can see here in the memory-based approach, the learning and the introspection-based approach is, well, it's not the same behavior. However, we can see that it is, well, kind of similar. I'm gonna say very similar, because I'm not showing that here, but in the paper as well, we have computed other metrics like, I don't know, the Pearson correlation or the mean square error, and we have seen that statistically they are quite similar. Okay, it's not just the plot, but if you look at the plot only, you can see that they behave quite similar. So what we believe is that the learning and the introspection-based approach are a more effective way to compute the probability of success in comparison to the memory-based approach, which was more, well, resource consuming. No, we have to say that we use this as a baseline because, well, this is exactly what happened. I mean, the real transitions are saved in the memory. So we know that that happens somehow. And these are, well, estimated in different ways. Now, this by learning, and this one computed directly from the Q value. When we use the 10% of stochasticity, we still consider the probability of success in general go down, but still the behavior between them are quite similar. Okay, so again, we believe that these approaches are a good alternative, an effective alternative to compute the probability of success. One last experiment. What if we start from the state 1, this one, using stochasticity as well? So why we wanted to observe, well, the behavior from here? Because, well, from that state, you also can take the action go left, which is, well, stepping into the aversive area or leaving out the flow. So, okay, so of course, clearly here we can see that the probability is near to 0. Okay, to conclude. Well, first we want to say that we have presented, well, 3 different explainable, reinforceable learning methods. Okay, the idea of these methods is to compute the probability of success in order to explain in a better way to non-expert end users why the robot decided to perform certain action from certain situations. Okay. Well, using the memory learning or introspection-based approaches allow us to compute the probability, this probability of success, and we believe that using this variable to inform the user the decision is a more human-like manner to express that. Okay. Therefore, well, this explanation can be provided in a more domain-based language. Well, certainly this is an ongoing work, and therefore there are many limitations that need to be addressed. And well, this also allow us for future directions and future work. So, well, one thing is, well, the explanation that I have shown here are just examples of possible answers. I mean, they are not automatically generated to any end user. So it's like we replace there only the probability of success. There are some other works addressing this issue, like the problem of verbalization. So of course, it's something that we need to somehow incorporate as well to our approach, we believe. Well, we also believe that we should use other more general methods. We have shown this first using tabular methods. Even though we believe that the learning-based approach and the introspection approach can be transferred directly to continuous domains, we are currently developing that kind of experiment. So using, well, things like function approximators, but also to make this method more general, we believe that we need to address other kind of tasks, like with different nature. For instance, here in this task, we have a terminal state. They are they are non-episodic tasks where you want to perform this as much as possible or as long as possible. So this kind of representation should be incorporated as well, which means that somehow as well to scale the approach to more complex scenarios in order to make this more valuable as well. Okay, well, thank you very much for listening. I think I have used longer than I wanted, but I think still there are some time for questions. I'm going to be online for the question as far as I know. So, well, thank you very much. I need to stop this now. Okay.